Hello, everyone, and welcome to this live virtual event brought to you by Aggregate Intellect. My name is Reza, and I'm excited to present to you today our invited guest speaker, Dr. Kai Hudek from IonQ. IonQ in the race to build a scalable quantum computer with trapped ion approach. Their approach has produced unmatched results. We'd love to hear from you guys, your questions, your comments. So please feel free to post them in the chat box and we will get to them at the end of this webinar. This webinar is being recorded by the Aggregate Intellect and the recorded version will be available later on their website. Now, without any further ado, I would like to introduce to you our guest. Kai earned his PhD from the University of Colorado in 2012, where he worked on Bose-Einstein condensates and developed technologies that's now on board of the ISS. This was followed by a postdoc at Duke University and a research scientist position at the University of Maryland, building trapped ion quantum computers. For the past 3 years, he has been a senior physicist at IonQ, leading system engineering. Thank you so much, Kai, for being here, for joining us, and for sharing your experience in quantum computing with us.
Yeah, thanks, Reza. Thank you for having me.
Mm-hmm. Of course, it's all yours. We would love to hear from you, and please share with us your presentation.
Yeah, thanks for having me again. And today I'm going to be talking about quantum computing generally and trying to answer the question of why people are interested in quantum computers, why we picked trapped ions, which seems very exotic, and then delve a little bit deeper into sort of ion trapping and IonQ's approach to a quantum computer. And just to start to orient you a little bit, what you're seeing here is a sort of state-of-the-art ion trap that has lithographically patterned electromagnetic features on this die here. For scale, this is about 1 centimeter on a side, and then superimposed over this is a chain of maybe 100 ions that we've trapped, but are really, really tiny, and you're sort of not going to be able to see them with your naked eye. So to start a little bit on the motivations of why quantum computing is exciting, I like to show this plot here, which shows the trend of Moore's law over the last 30 years. And of course, as everybody knows, this trend has been slowing down. And the interesting thing, one way to think about maybe why that is, among others, is that as you get smaller and smaller on the transistor roadmap, you've actually come to a size where each transistor is a countable number of atoms wide. And that's really amazing. But of course, it makes perfect sense that if you were to try and build a transistor out of a single atom, we know that single atoms do not behave the way you might expect a classical system like a transistor to behave. The good news is that, this quote from Richard Feynman, who was one of the original people to suggest the idea of using quantum mechanics for computation back in 1982, said that if you really think about it, when you go down to single atom scales or very, very tiny things where quantum mechanics dominate as opposed to are masked, you actually get a whole new opportunity for design, and you might actually be able to create new things. And of course, being a scientist, Feynman loved a big scientific challenge. And so, even without Moore's law ending, there is an exciting part to quantum computing that, in theory, in principle, it can solve problems that conventional approaches would actually never be able to solve. So if we start with, where we are today or where we were a couple of years ago, quantum supremacy, that's a term you might have heard in the news. It was quite controversial because Google put out this quantum supremacy paper saying it had done something nobody could do. IBM said that they could do it. But there's some subtlety to that. And as computing, as the difference between a physicist and maybe a computer scientist, I thought that we could delve into this plot here, which comes from that paper, which I actually really like. So on the x-axis here, you have number of qubits, and then you have on the top, you might have memory requirements. And then you have contour plots that are time, time to run your circuit. And the way that you would simulate something that can't be simulated, right, which is what quantum supremacy says, is that what Google did is they marched their way up in qubit number and verified on a supercomputer that the results of their quantum computer were accurate. And then they jumped over here to 53 qubits and said, look, we did something that nobody could do. And what you'll notice here, the subtlety of can you do it classically versus can you do it quantum mechanically does not really exist until you hit this purple line. But if you were to take a laptop, you would need a million cores and 10 terabytes of RAM just to get your computation down under a year on a laptop. And if you wanted to actually do what IBM suggested and simulate the 53 qubit quantum supremacy model that Google did, you would need, a memory upgrade to the world's fastest supercomputer and possibly a nuclear reactor to run it. So, the subtlety of quantum supremacy and quantum computing, even in today's world, means that maybe it's possible, but there is that nuance of is it useful? Is it cost effective? Can we make it do something in a way that you can replace a supercomputer? So, we're already at the stage where we're sort of on the edge of quantum computers doing something that can be done, but is not easy. And then if we look further into the future, there is what gets people really excited is this promise of things that will never, ever be able to be done. So I have here a picture of the traveling salesman problem and, an artist's rendition, of course, of some random material structure. And, just back of the envelope for the traveling salesman problem, to solve it, it very quickly exponentially grows to say more atoms. There are more paths in this, nodal structure than there are in the atoms of the universe, or more configurations of some very simple molecular structure than there are number of bits in the world's hard drives. So that's the future-looking promise that gets people really excited about quantum computing. So how do quantum computers differ from classical computers? They differ in two ways. One is the qubit versus the conventional bit, which is sort of artistically shown here. A conventional bit, as we all know, can exist in a state 1 or a 0. And of course, you've probably all heard that qubits can exist in both 1 and 0 at the same time. And this, along with a quantum resource that you have that's called entanglement, this actually gives you exponential storage capacity. And why the storage aspect of it is important is that if you look at a classical algorithm, you always have n bits. You have n bits on your input, you're doing your operations or computations on n bits, and then you have n bits on your output. But in a quantum computer, you have n qubits, you have 2 to the power n, so an exponential space in which you can compute on, and then you only have n out bits. And so this exponential computation is really what gives you an advantage from quantum over classical. But the difficulty is, of course, you only have n bits in, n bits out. So how do you design your quantum algorithm to really orchestrate this quantum interference, this sort of quantum mechanical structure, so that unlike in a classical thing, you can just read out all the bits. You have to be able to read out an exponentially small number of answers compared to your computation space. And so you need them to collapse onto the state that you want. And that's sort of the challenge of quantum algorithms, which is why classical computation and quantum computation are not one-to-one, but quantum computation does have the potential to access very large markets. So, this Gartner is a consulting firm, and they put together this bubble map of all of the potential things that the quantum ecosphere could potentially hit, not just computation, but there's quantum communication, there's climate change and nitrogen fixation. Machine learning is a big category that we actually think is one of the more near-term applications. And then the thing, of course, that kicked it all off was, say, code breaking, Shor's algorithm back in '95, showing that a quantum computer of sufficient power could actually break RSA, and then or the math behind RSA, and could actually sort of lead to all sorts of things that governments and businesses don't really want. And so we're excited that the total accessible market for things like molecular design, quantum chemistry, or chemical processing, nitrogen fixation, or logistics and navigation, or even market optimization, portfolio optimization, those are very, very large markets. And so for quantum computing to make even a small dent into any of those markets would be a big sort of a very big effect commercially. But I will say that you shouldn't be fooled by the moniker computer. When you think of a quantum computer, do not think of your desktop. This quote from Bill Phillips, who's a Nobel laureate, says that a quantum computer will differ more from a classical computer than a classical computer differs from an abacus. And this is very appropriate for the state in which we find ourselves in quantum computing. So here is a list of some of the leading contenders for a quantum computer. And you'll notice that even at a physical layer, they're all completely different. And the reason is because we are at a time in quantum computing where we're sort of pre-silicon back in the 50s for the transistor, where we didn't know what the actual best physical qubit layer is. So of the leading contenders, there are superconducting loops, which is essentially a nonlinear LC resonator. This is what it actually looks like. I think this is a chip from IBM, and it probably has 1, 2, 3, 4, 5, 6 qubits on them. This is a 6-qubit chip from IBM, but Google as well, and Rigetti is a smaller company, but sort of the big players seem to really like superconducting because they actually get to leverage a lot of the same silicon technology that they have now. There are, of course, trapped ions. Shown here is an artist's rendition of a different style of ion trap with lasers and cameras and an actual picture of ions. This is what I'll talk about more later, but then, the last sort of leading contender is a silicon quantum dot where they trap individual electrons. Diamond vacancies are a little bit further out, and of course, topological qubits are sort of this holy grail that Microsoft has championed, even though there has been some news recently that they had to retract the paper, and there's been a little bit of a snafu about the actual existence of these. So, there's a whole hierarchy of technology maturities right now, and superconducting and trapped ions are certainly the top two. Now, part of the reason that we are championing trapped ions when a lot of the bigger players are actually championing superconductors is a little bit summed up in this plot where, one of our co-founders, Chris Monroe, has a saying that we don't do physics, we just do engineering. And of course, there's a lot of subtlety to that statement, and it's a very bold statement. But generally speaking, ions are quantum, they're atomic clocks, essentially. So, they are perfect and replicable, and the challenge is to keep them perfect and replicable. And, generally speaking, the ion trap technology has shown sort of all of the things you might need from top-level scalable system architecture all the way down to, like I said, a perfect replicable qubit. All of the things needed to sort of build this scalable quantum computer that will be commercially useful and really sort of world-changing. So some things I didn't talk about, like neutral atoms and photonic circuits, all of them have now, if you talk to them, they would disagree with this, but we think all of them have either fundamental flaws or just a bunch of unknowns that require fundamental scientific breakthrough, as opposed to very, very, very challenging engineering tasks. And I will not say that our roadmap is not technically challenging. I just wanted to sort of say, to point out one of the counterintuitive things about ions that's actually a very large advantage from a computational space is that even though our ions look like they are in a line, and all of the pictures I will show you today show them in a line, because of the way that we physically interact with these qubits, they actually get full connectivity. So if you look at this graph, we have, say, 3 superconducting chips from IBM, Google, and Rigetti. And what you see here are dots are qubits, and lines are actually physical connections. And this is laid out the way you would expect. It's a 2-dimensional chip. It's got patterned qubits on it. It has patterned wires on them. And so as such, because a 2-dimensional chip needs some level of connectivity, you can see that these lines are limited in their scope. And so for this qubit, for instance, to talk to this qubit, it has to transport its quantum information all the way around the circle. And of course, that's very inefficient and very error prone at this time. However, our qubits are held in an electromagnetic trap. We use ions because ions talk to each other through the Coulomb force. And this trap, even though it looks one-dimensional, actually has long-range interactions. And it's it actually has what you might call an electromagnetic bus, right? Like a backbone communication line. Because our wires, because they aren't physical, they're actually laser beams. We're able to get this full connectivity, and we can do real-time programming. This is much more like an FPGA, where we can set the topology of this to be whatever we want in real time based on the algorithm that we're running. And this is shown, let's say, in order to demonstrate this. We have this we partnered with universities to get this benchmarking paper to do a bunch of what you might call benchmarking algorithms, sort of Bernstein-Basrani, and some non-trivial gate things. And as you can see, for instance, when you get to a certain level of connectivity or a certain size, some of the current superconducting architectures cannot keep up. Now, this is not, let's say, the Google Sycamore 53-qubit chip. This is just a subset of chips. But for this particular paper, for this particular study, IonQ's, the trapped ion technology outperformed all contenders, and sometimes a lot of them couldn't even achieve, in their current state of the art, could not achieve a successful outcome. So that hopefully convinced you why quantum computing is important and why trapped ions are obviously the best, right? Of course. But if not, that's okay. We'll dive into sort of how this technology works, what IonQ is doing, and the fun scientific stuff of how to make an ion trap quantum computer. So the quantum system is one of the reasons it's very difficult is it's the most delicate type of system in the universe in some sense. And so it really needs to be isolated from all their environments. And because we're trapping individual particles, we need to first isolate them from the 10 to the 23 atoms that are in the air all around us, right? And so what we do is build, this is a traditional sort of ultra high vacuum chamber. It's got pumps, it's got optical access, it's got electrical feed throughs, it's got mechanical structures, all of that type of stuff. This is on a 1-inch grid, so this is about 8 inches across, just to get yourself a sense of scale. Typically, these things cost, tens of thousands of dollars, depending on the types of components. It takes a few weeks of processing, and a lot of time and effort goes into it. But at the end of the day, we can get pretty impressive numbers, right? So we can remove basically 10 to the 12 or 100 trillion times lower pressure than ambient room pressure. And that's just where we start. Once you've got your vacuum set up, you need to actually create these individual ions and then get them into your trap. So our atom of choice is ytterbium. That, if you've never heard of it, it's YB, and it's all the way down at the bottom right of the periodic table. We start with a neutral atom and evaporate that just ever so slightly into our trapping region. And then we use these combination of lasers to strip off the outer electron to turn it from a neutral atom into an ion. We then use the same lasers, in this case 369 nanometers or near UV lasers, to turn it, to cool it to millikelvin temperatures. And actually, it's kind of funny when one of the things we say is that we operate at room temperature, but our ions are actually colder than the dilution refrigerators that you can get for superconducting loops and some of these other technologies needed. And it's super counterintuitive to think that you could create an ultra cold atomic sample with lasers, right? A laser imparts energy, a laser is hot, but it only took a few Nobel Prizes to figure that one out. So it works, and it's the basis of this whole field. And then, the challenging part, but also, still just strictly sort of engineering, is you need a bunch of other colors from UV up to visible and infrared. But you can manipulate all these different states, and there's actually a complexity that, if you're clever about it, you can take advantage of for your computational structure. So we have our vacuum system, and we have our ion, and we have our cooling lasers and all of that, and it's there. So how do we keep that ion in space? In order to trap that ion, as I alluded to before, you need an electromagnetic bottle, essentially, in order to physically keep these ions floating in space, untouched by objects, untouched by background gases, untouched by anything, stray photons that you might not want. The structure of this, from a sort of intuitive perspective, is basically a three-dimensional bottle. So you've got a combination of DC electrodes, shown here maybe as these two pluses, and then RF electrodes that create an oscillating quadrupole potential here. And the reason that you need RF is that Maxwell's equations say that you can't really create an electromagnetic maximum in free space, minimum in free space. So you need to make what's called a pseudopotential, and this creates this is what it actually physically looks like, and this is how you can trap these ions in a chain. And if you look closely, the ions are not all evenly spaced, and that's because we've created an electromagnetic bottle, we've created a bunch of ions, and when you put them in, they distribute themselves like masses on a spring, right? So these masses in the middle are compressed tighter than these ones on the end, and this is all very well described by theory. And if you take this three-dimensional structure and actually do a sort of a conformal mapping to a two-dimensional surface, then you get to take advantage of all the fun advances in lithographic techniques and chip-making techniques to create what I showed you on the first slide, which is called a surface trap. And so unlike superconductors, we don't actually use lithography to define our qubits, but we do take advantage of that advanced manufacturing to define the control electronics and our ability to sort of manipulate the degrees of freedom. And so that's why these are super important for state-of-the-art quantum computers. And that's it. Those are the three main characteristics you need to physical systems you need to trap an ion. You've got vacuum, you've got lasers, and you've got an electromagnetic bottle. If we want to dig into now the physics sort of the ion itself, we are building all qubits, essentially all of these exotic technologies. The main goal is to just get an isolated quantum mechanical two-level system. And so you would think there's a lot out there, but it turns out only a few of them seem practical. I mean, so when you take all of the different needs of a quantum computer into account. Ours are the two different ground state levels of this ytterbium atom. So our qubit 1, or what we call the upstate, is this atomic level, and our downstate is this atomic level. And as I said before, these are basically atomic clock states, and so they're naturally very well isolated from the environment. If you think about it in terms of coherence times, or the amount of time that this qubit takes to lose its quantumness, it's sort of much longer than what you get from a superconducting qubit, because it's an item floating in space versus a physical device living in a noisy chip environment. We use lasers to manipulate these atoms in all sorts of ways. So in order to detect the qubit state, we actually use a laser to detect this one state. If the qubit is in the one state, this near UV laser excites the atom, and then it fluoresces and decays, and you can collect a histogram of photons to detect that this qubit is in the one state or the upstate. And if it happens to be in the zero state, that same laser will not detect that. That same laser will not cause the qubit to emit photons. And then if you put a discriminator in here, you can do some fancy computational techniques, or a very straightforward way. You can get very, very high state detection fidelity and in order to read out your quantum register. If you want to do gates or manipulations on, do the actual computations, there's a couple different ways that you can manipulate this ion. The first way is microwaves, where you're basically flip-flopping the 1 and the 0 state. So think of this as like a NOT gate, or a continuous version of the NOT gate. It's called Rabi flopping. And what you can see is that going from 0 to 1, it's from the 0 state to 1 state and back over as a function of time makes this nice, beautiful sine wave. And sort of state-of-the-art error rates for this type of gate around sort of 10 to the minus 6 level. And just for reference, Most places like Google, IBM, or are at sort of the 10 to the minus 3 level, 10 to the minus 2.5 level. And that plays in when you come into error correction. That high fidelity gates are one of those things that everybody is sort of searching for. The other way that you can manipulate the qubit to do gates on it is with what's called a Raman transition or an optical transition. It's the nice thing about ytterbium is we're able to use a commercial laser, triple YAG 355 nanometers. It's a 2-photon process that basically virtually excites between these two levels. And this has been shown to sort of see more of the 10 to the minus 4 level, 10 to the minus 3 level. And this is the way that we have chosen to do the majority of our interactions, because in order to get, lasers seem inherently worse because they have lower fidelity, but they have two main advantages, which is speed and individual addressing. And so, of course, it makes perfect sense that if you want to do a computation, you need to be able to address all of your qubits. And so this is actually a picture of what it might look like. We have our chain of qubits. We have lasers coming in from the side, and turning on two beams can entangle any pair of ions. And the way that it actually sort of looks is this cartoon where we take 32 beams, for instance, and pass it through a multi-channel modulator that gives you full phase, frequency, amplitude control on your control lines, and then use an optical system to project that down over onto this chip that you can see here, sort of the cartoon of the chip I showed you before. So in this way, we shape our optical setup in order to give us this full connectivity. And this is, again, a cartoon of what we have it. And just to help picture what this actually looks like, there is a very nice analogy to the digital circuit. So the superconducting qubits look a lot more like this, where you have an actual printed circuit and everything is wired together physically. Now, what gates you do can be done on the fly, right? Because sort of you have this continuous space, but the connections are straightforward. Here, like I said before, we can, on the fly, change our connectivity just based on how many laser beams we turn on and off, and on which ions we turn them on and off. And you can write out a quantum circuit that looks, basically identical to what you might expect from a digital circuit. And so we like to call it sort of, this is more of like an FPGA mode, where it's reconfigurable on the fly, optimizable for the algorithm and circuit you want. And this might be more like an ASIC or something like that, which is not a bad thing necessarily, but for making a more general quantum computer, there's a lot of advantages to being able to wire it up on the fly. And so just to walk through a little animation of what this might be, we have our ion chain here, and we have sort of an example circuit here. Now, there are more ions in this picture, so don't look too closely. 1-to-1 are qubits, but typically when you look at these diagrams, the qubits are on the vertical axis, and then time and gates are on the horizontal axis here. So this is sort of like the qubit lifetime inside of a circuit. And so we start with state initialization. This could be thought of as a reset operation. We want all of our qubits to start in the 0 state. It's just sort of, you're resetting your register. We can do that with a global operation, so we can do that in one shot. Then we can turn on a pair of laser beams to do individual addressing and to do, say, a 2-qubit gate to generate entanglement. We can do single qubit gate rotations, different 2-qubit gates, different 2-qubit gates, and so on and so forth. And then at the end, we can just do a single shot readout of the quantum register. And that's basically, at a very simple level, the order of operations. Now, so that's part of the talk, was basically talking about the physical layer and the physical hardware layer. And that's where my expertise comes in. IonQ is first and foremost a hardware company, because we feel that at this stage of quantum development, the real innovation, the real sort of value add is from the hardware, because that's where we don't know. That's where the engineering really needs to come in. But so I talked, of course, about the ion trap itself and the optical system itself, and sort of the electromagnetic bottle and lasers you need for doing qubit control and qubit management, the detection process where we actually look at ion fluorescence to read the system out, and this gate laser control to do the actual computation and measurement. And sort of at a fundamental level, that all works great. But of course, to do complicated real things, you need to automate that. You need to integrate that into a stack. You need to optimize your circuits. You need to run calibrations. You need to do all of this stuff. And so IonQ as a company has focused on what we call sort of the full stack. So, one level up from the physical hardware of lasers and vacuum systems is the custom electronics and system controller stuff. So we do everything from ultra low noise, DAC systems to high speed FPGAs. And then above that, of course, is our own custom software stack, custom quantum languages, compilers, things that are optimized, because at this point in the day, where quantum systems are, you need heavily integrated, heavily tailored systems to really squeeze the most out of your system. And then above that, we have our cloud user interface. And so if you don't know, we are currently live on AWS and Azure and fully integrated with our APIs. So you can go sign up for a AWS or Azure account, Microsoft Azure account, and run a circuit, or try out this hardware yourself. And so this is sort of, we do a lot of stuff. We do a lot of stuff at IonQ trying to make the full realizable quantum computer. And so just to dive into some of the things we've been able to accomplish so far using this full utilized stack, we ran a few benchmark algorithms. These are state-of-the-art, sort of peer-reviewed, Nature Communications 2019. We ran a couple of what we thought were canonical algorithms. The Bernstein-Vazirani is one that we like because it sort of showcases full connectivity of the circuit, and the sort of it's a bit of a toy algorithm that's shown here on the left. The thing that makes it quantum versus classical is that classical you need n queries, where basically you would just send in your basis states 1000001000 to probe the output of this unknown circuit. But in quantum mechanics, you really only need a single query, and that's shown here, where for a 10 qubit system, you get 2 to the 10 possible outputs, or 1024. And with a single shot, rather than opposed to n shots, we were able to successfully get the right answer, greater than 50% of the time across all of them. It's upwards of, above 90% on some. And this periodicity you see actually speaks to some of the systematics in our system that we're working out, of course. And that's actually shown also here on the next slide, a significantly more complicated benchmark algorithm, the hidden shift algorithm, which sort of the mathematical goal of that is shown here. Classically, it requires square root of 2 to the n queries. So this is a bigger speed up, because quantum you only require one query. And our ability to discriminate is shown here, where you have your 1024 input states and your 1024 output states. And of course, in this case, we want this diagonal line to be 100%. And you can see that we have some sort of below 10% noise on all of the other possible 1 million output states. And this banded noise structure is, again, just speaking to some systematics. But this was an algorithm that was sort of first of its kind, at least to the scale that we were able to do it in 2019. We also ran what we're calling a Pathfinder application. So the previous benchmarking algorithms were a bit more proof of principle and demonstration algorithms. Quantum chemistry is, of course, a real application for quantum computing. And it has a lot of sort of real world applications, like chemical reaction rate, catalysis design, molecular design in the far future, that type of thing. And it also fits under a broader class of optimization problems with exponential speed up. The state of quantum computing is not as exciting as, say, this molecule here, but we started with a much simpler molecule, water, or H2O. This table just sort of shows how you might get from, work your way down in accuracy to the sort of target accuracy, or chemical accuracy, as they call it here, down at the bottom. And that sort of requires, this, like 19 terms, 12 qubits, 166 gates. And we were sort of stuck up in the top few terms. But this was on the very first system that IonQ ever built, and we are currently on system 5. So our capabilities, now we haven't gone back to run this exact paper, but our capabilities have been expanding. And it's slightly more impressive when you look at similar experiments that were done on other systems for different molecules, but similar size, similar scope, similar scale. The fact that ours, as we added more terms, our simulation actually followed the the theory trend line as opposed to diverging rapidly is actually fairly impressive. And so we were sort of happy with these results, even if we couldn't get to the level we wanted to at that time. And so, where we are now is 2021. This is the roadmap. We're on our 5th generation system. The latest published results that we can really talk about, besides what we've talked about on, publicly in AWS and all of that, are, we're on our 5th generation system talking about 22 algorithmic qubits. We're sort of progressing up this qubit count chain, and it looks relatively flat. We do think that there are reasons that we think we can get. Machine learning is actually going to be one of the first sort of applications that can take advantage of the small number of qubits. I will admit that I am not an expert in this, but we do have Sonika Jory, who has given several talks on this, and so we have an in-house expert that I'm sure would love to answer your questions at some future date. The reason that this sort of looks flat is that because behind the scenes, there's an inflection point where this double blue star indicates error correction. And I did not talk at all about error correction, but that is sort of a critical function that is going to be necessary to really scale these systems up and take advantage of both exponential computing power, but also exponential growth in your qubit count, in your fidelity, and in your metrics for making a scalable quantum computer. And so, we think that the 2020s are going to be a very exciting time, and we have a very aggressive roadmap to, be the world leader in quantum computing and sort of stay that way. And so just, I'll end a little bit with a Silicon Valley joke, but we're a startup company building full stack quantum computers. We've only been around for a small handful of years. We were founded in 2015, but we sort of were incubating a little bit and have really been kicking off for the last 4 years. We're up to over 50 employees. And we've raised $80 million. We obviously have not spent all that because we're still in business. But we're commercially available. We're on AWS, we're on Microsoft Azure. We have next generation systems coming up. Here's a picture of System 5. It's come a long way from the physics experiments where we started, and we're competitive with the big players. We're competitive with IBM. We think we're better than IBM and Google and all of that. So, the bang for your buck that IonQ gives you and the things we think we've accomplished, we're really proud of. And, just put it out there that we're hiring. We need all sorts of expertise. Quantum computing is a very broad, very cross-functional discipline, and it needs expertise and new ideas from all corners. So with that, I'll wrap up and take any questions or anything else.
Wonderful. Thank you very much, Kai. Thank you, and congratulations really to you and to IonQ team for accomplishing such amazing job in such a short time. As a relatively small startup, you guys achieved really, really sophisticated engineering and control over quantum systems. So congratulations. Thank you very much, guys. We are available on YouTube. If you have any questions, please post those questions there. I will read them to Kai. So first question, I think just about what you said in this slide that we are still on it. You mentioned that you guys are hiring. That's a great question, because when it comes to great point to raise, actually, because in quantum technologies, a lot of people think that you must be like expert in quantum mechanics, let's say, or definitely a physicist to be able to work in that field, which I know it's not very accurate term. So you tell us, as an expert in that industry, that what kinds of basically skills you think young people, students, perhaps even undergraduate students, can look for or look into to achieve those skills if they want to basically land a job in quantum technologies, quantum computing.
Yeah, that's a great question, and actually, it's something that our co-founder Chris Monroe has been spearheading with the U.S. government for a while now, right? That the quantum workforce, the quantum ready workforce, is it's not there, right? The ecosystem is speeding ahead, and I think that the opportunities in general are very good because I think the supply is less than the demand, or it will be in the coming years. From my perspective as a hardware engineer, I know that I am a physicist, but I work a lot in the engineering side of things these days. I think that the need for quantum, the need for these cross-functional people who speak the language of quantum but have done really deep precision engineering or system development or that type of stuff is where I see the needs fall short, right? So when I'm looking for hiring, I'm looking for expert optical engineers, expert mechanical engineers, low noise control systems engineers, FPGA engineers. Like the challenges that we are tackling are very, very physics driven, right? The specs cannot be pulled off a spec sheet. They cannot be inferred from other things. So having that ability to talk the language of quantum physics and to know what's important and what designs need to happen. But what I'm really excited about is pulling in all of that other expertise as well. I mean, I want people who have built satellites. I want people who have built telescopes. I want people who have built, worked for Intel. Like there are so many different categories. Actually, I think that if you're a student, physics will always be there, right? I mean, the nobody knows how to build one of these things, right? 2030 hits, nobody has any realistic idea of what this thing is going to look like. But we have a roadmap. We have we're going to attack that problem just like everybody else is going to attack that problem. Right? Google put out a roadmap. They all look very fanciful. So there is a lot of very challenging physics, applied physics, those type of things. And so, I wouldn't discourage people from going into physics or getting a PhD because you never know what's going to be important. And my opinion about a PhD is it's not necessarily what you do exactly, but learning how to think differently and learning how to problem solve is one of the main advantages. So, I don't, because there's no winner yet of ions versus superconductors. Maybe topological comes out on top out of left field. I can't really say what skills, generally speaking, are important. But learning the language and doing some, this is a very complex, precise, delicate system. So those type of skills in general, engineering, hard engineering. I don't have a good answer because I think it's a national level issue that people are trying to solve.
Great. Yeah, I can summarize it as basically we need people with cross-disciplinary skills and expertise who understand the physics of what's happening, and at the same time they have all those really good high-level engineering skills as well that can be basically integrated in a very sophisticated machine like that. Basically.
Yeah.
Also, of course, we need always, software people with,
Yes.
machine learning background that they can use this machine. At the end of the day, the way that we talk to these machines won't be very different, I assume, from what we are doing right now, right?
Yeah, that's the goal. But and you raise a good point. I think that there's lots, for those who are more computer science minded and theory minded, I think there will be a lot of demand for quantum algorithms research, quantum compiler research, that kernel level of the stack. Of course, there are several companies that exist now that are doing that are also doing like the API type of stuff and sort of the UX type of things so that, JP Morgan can come in and optimize a portfolio. But, that there is a lot of space in that stack for people to come in. And I know that field is much, much smaller than I think what is needed to support the growing number of hardware platforms and the growing demand for these type of things. And that's a good space to get into because it's very interesting. It's very challenging. And there's, I think, Peter Shore, who sort of kicked off the modern era of quantum computing, made a statement in a talk once that, there's a reason that we're still talking about Shor's algorithm 20 years later, because there are probably 60 people working on quantum algorithms, professionally, whereas there are 60,000, classical computing algorithms people. And so it's not, the disparity of creative thought, of actual just brute force thinking, it's obvious that needs to grow. So.
Absolutely. It's a great point, actually, Kai, because yes, the most successful algorithm that we have after 20 years is still that Shor's algorithm. So there's still plenty of room, I guess, to play, and smart people can come up with, other applications and other algorithms that can successfully basically harness this power of, quantum communication when it comes that we have hardware powerful enough to run big algorithms.
Yeah.
Wonderful. So yes, plenty of space is still available, I guess, in that department as well. Great. So maybe another question related to this slide is you guys started as a startup, which is wonderful. The idea of basically moving these things out of academic labs into a real world space and then raising funding for it, and build this sophisticated machine outside, the government grants and helps from different funding agencies. How is that journey, and what are the challenges of building a quantum computing hardware startup that you experienced or you felt or heard from people at IonQ?
Yeah, I'll start with the exciting part where, I think working for a startup, I used to describe it as the best of both worlds, right? So you get to work on these really amazing cutting edge challenges. You get to work with a big team, and you get to work with a lot of resources. Whereas in academia, it's small teams, limited resources. The two trade-offs you make are time. So in academia, you have the time, and also sort of the direction, right? So in the startup world, we are able to accomplish a lot of things, but for those who like exploring all of the unknowns and being really super conscientious about it, unfortunately, there's just not enough time, right? Like you find something interesting and you have to move on. Whereas in academia, you could explore that and sort of satisfy your intellectual desires. There's still plenty of that here, right? Because there are tons of challenges, but you don't get to publish, you don't get to do a lot of the things. So that transition, especially for PhD physicists, was a bit challenging. But for me, I really just enjoyed the other aspect of it, that I was, this type of system is just too big and too complicated. The European Union is trying to build, has collaborations to build these type of things. It's that type of scale where if you were to do it in academia, you'd have to. And I think what they're doing is absolutely fantastic. They've come up, they've published a lot of great results. It's just a different scale and a different time and that type of thing. So, the speed at which you can do things is great, but then of course the pressure to deliver is also very challenging. And it's a change in mindset. It's a different ecosystem with business and with, deliveries and all of that type of stuff. So I find it very exciting, and it fits my sort of personality. But
no, absolutely, I agree. I bet it is very exciting. How is basically a side question? How's fundraising affected by all this, past 1 year and everything that happened for a quantum computing startup?
Are you saying specifically? I mean, generally speaking, the market is very excited about quantum, right? I mean, It's in the news. All of the big players are talking about it. Even the finance people are talking about it now, right? Banks are talking about how it can do portfolio optimization. BMW, all these big companies are excited about it. And then, of course, all of the national governments are excited about it as well. Germany, the EU, China, the US. So in that sense, I think, generally speaking, fundraising is great at the moment. And so, we at $80 million raised currently, I think we're probably the well, third biggest startup, certainly the biggest ion trap startup. I know that Rigetti in the superconductor space has raised more money than us, and Psi Quantum in the photonic quantum space has raised more money. But for us, it's been great so far, I guess.
Wonderful. Glad really to hear that. It's great that there is still, all the attention and funding for this really exciting technology that is coming up. Basically, another question is, what's the biggest challenge for you guys as using this Ion platform for scalability? You mentioned, I think, 22 qubits right now, right? Is that the state of the art? Yes. So what basically what challenges you should overcome if you want to have more qubits?
Yeah, there's a lot of sort of technical challenges that are limiting this number. But what I would say at a high level is that it's not the number of qubits that we can trap. So I showed, at the beginning, this picture where we can trap 100 qubits, and we can do gates and implementations, sort of laser implementations on more than 22 qubits. But in order to get something quantum, you need to be able to entangle all of those qubits and to really take full advantage of this exponential space. And so it turns out if you just do, so quantum volume is a metric that IBM came up with, and there's sort of like a nice, easy, quantifiable thing it's not super nuanced, but you can either at a high level, you can either be limited by the number of qubits or you can be limited by the gate fidelity. And so 22 is the number of qubits that you can have where you need 99.9% gate fidelity, essentially, right? So if you the math would say that if I have more than 22 qubits but only 99.9% gate fidelity, then those other qubits are wasted in some sense, or they're not fully utilizable. And if I have greater gate fidelity, then I'm limited by the number of qubits. And so we've defined algorithmic qubit as basically the number of, so a different framing to say the number of usable qubits. So when Google says they have 53, but they don't have 99.99% gate fidelity, then they are not taking full advantage of that qubit space. So we have arranged our roadmap and our technical sort of approach around this idea that we're currently fidelity limited, so we're going to push on certain aspects of the technology that's not specifically qubit number. However, right, once that's not to say that we're not doing that in the background, but that's not the top line number, because when we hit 64 here in 2025, you can see that this is 16 to 1 error correcting code. So really, we're at physically 35 qubits. But when we say we're at 64 qubits with error correction, we're at 64 times 16. So behind the scenes, we've actually we'll be working on increasing the number of physical qubits, as well as the topology and layout and all these other things you need, by a factor of 10, let's say, right? So.
Okay. So there is still some technical challenges to overcome to take advantage of the whole quantumness of the system, basically.
Yes.
You mentioned the other player in the Ion Trap, basically the game is the Honeywell. How is their technology different from IonQ technology?
So their technology uses something called a quantum CCD. So essentially, they are using physical. So our physical system looks like this and achieves this type of connectivity, and their physical system looks more like looks maybe more like this, right, where they have smaller subsets, and actually, really, they only do 2 qubits at a time, and so they use these surface traps to physically manipulate the location of smaller subsections of their quantum computer in order to achieve this full connectivity, scalability, and all these 2 checkboxes here. So it's essentially the way that they choose to trap and manipulate the physical ions and then address them with their lasers and other readout and gate mechanisms. But fundamentally, the physics is the same. the system looks from the outside 99% the same, vacuum, lasers, etc. They just sort of lose out a little bit on that. And so we think that for a variety of reasons, sort of more architectural and computational reasons, that are the way that we're doing things is superior. But they're very, very similar. That's right.
Okay. Similar technologies, intrinsic. And on the number of qubits, how do you compare the two players?
So I think their latest, I don't have a slide on it, their latest number is 6, maybe 10. It's if they have 10, they haven't published the quantum volume number for that, but essentially they're doing their qubits pairwise, and so they have a 6-qubit computer, but they have to sort of do some fun manipulations. So I'm sure that was a year ago. I'm sure they're well beyond 6 qubits now, but I don't have insight into that.
Okay. Wonderful. Thank you very much, Kai. As the last question, I will ask you just one more question, and that's about, you mentioned you guys need very high vacuum, basically.
Mm-hmm.
And comparing to what people do in the superconducting world, they need like millikelvin region.
Mm-hmm.
How do you compare these two technologies, reaching to ultra high vacuum versus reaching to ultra cold, and on the cost side?
Yeah, let's see if I can. I wonder if I have a slide on this.
You had one about the ultra high vacuum. Yeah.
So this is a slightly different thing. So the thing about the dilution refrigerator, it really comes in terms of scalability, right? And it's a different, fundamental physical challenge, and it's sort of summed up in this picture here, where in order to scale a quantum computer, right, they run into a lot of challenges, because basically the world is hot and they're trying to suck a bunch of heat out of it, and that has to happen all the time, and that has to happen while operating a quantum computer. For us, the world is full of air molecules, but we suck them out once, and then you just put up a wall and they're out sort of forever, right? We need some level of pumping, but it's not the same. So sort of the physical scope of the two challenges are different. For IBM, this is a real picture they put out, last year sometime. For them to scale up, not to infinite qubits, but from what they have now to like the 1,000 qubits they want, they have to build this type of system. And so if they want to double that, they have to build 2 of these systems, and then they have to figure out how. There's a physical limit to how big you can make a dilution refrigerator, because you're really it's a really amazing technology, pulling heat out to get physical devices down to millikelvin temperatures, but we think that it sort of has a fundamental scaling limit. That I'm sure there was a paper about how you can pass quantum information from one dilution refrigerator to the other and stuff like that. But the scale is different, because what we can do is actually go the other way, right? That in terms of you can build one of these, we can build 10 of these. And this is sort of the picture that I was showing before, where this is maybe 1.5 inches on a side. And this is a real device that is trapping, it has challenges, it has limitations. There's a reason we're not using that today. But the sort of proof of principle of a 14-foot, 10,000-pound dilution refrigerator versus a 1.5 inch, this is just part of the system. This is just the vacuum part of the system. But that sort of hopefully explains the magnitude of the two different challenges.
Exactly. Thank you very much. Yes, that's the whole point. That dilution refrigerators are huge. They're bulky, very expensive, very complicated technology that goes into like cooling those superconducting chips. And here you guys don't have to deal with that. Wonderful. Thank you very much, Kai. I really appreciate your time and telling us about great technologies that IonQ is developing. I really, really appreciate it. And thank you everyone that could join us today from all around the world. We always try to bring you amazing speakers like Kai to educate us, to inspire us about quantum technologies and what they have to offer. Please check the Aggregate Intellect webpage, and they have the list of future events and talks. And by that, I let you guys go, and I let you go back to developing all these great technologies, Kai. Thank you, and have a great day, great night, wherever you are, guys. Thank you.